Let's now talk about the line notation for electrochemical cells, which just gives us another way that we can represent the reactions that are occurring. In the line notation, what we're going to do is always put the anode on the left-hand side and put the cathode on the right-hand side. These two get separated with a double vertical line, and the double vertical line represents the salt bridge. We'll consider an example where we have the following cell. At the anode, zinc is being oxidized to zinc 2+, and at the cathode, Ag+ is being reduced to Ag solid. The way that we would represent this cell in line notation would be as follows. We put the anode on the left-hand side, so we're going to say that is our half reaction that involves zinc going to zinc 2+. What we're going to do is read the equations always going from left to right. So in this reaction at the anode, zinc goes to zinc 2+, and so in the notation we write zinc first and then zinc 2+ second. Additionally, we drop a single vertical line in here if these two species are in different phases. Zinc is in the solid phase, zinc 2+ is in the aqueous phase, and so to distinguish between these two different phases, to show that there is a separation between the two phases, we use a single vertical line there. That's how we would write the anode. Then we put the double vertical line to represent the salt bridge. And then on the right-hand side, we'll put in the cathode. Again, we always read from left to right. So in the half reaction that occurs at the cathode, Ag+ goes to Ag. And so we'll write Ag+, Ag. Now, Ag+ and Ag are in different phases. One is aqueous and one is solid. And so you use a single vertical line to separate that. It is unnecessary to balance charge when you're writing the notation in this format, so it's not necessary to include coefficients, it's not necessary for you to balance the electrons between the two half reactions or anything like that. The idea behind this notation is to provide, in the minimum amount of information, exactly what's occurring in this cell. And with what's written here, you can figure out exactly what the half reactions are, and you can figure out exactly what the coefficients should be if you were to go and rebalance the equation. Let's take a look at an example where you can work backwards and convert the line notation into reactions. We're going to identify the reactions that are consistent with the line notation Al, Al3+, Cu2+, Cu. So it's important to remember that the left-hand side of the equation represents the anode. And remember from our mnemonic anox red cat, anode means oxidation. So that will be our oxidation half reaction. The right-hand side represents the cathode. And anox red cat, reduction occurs at the cathode. All right, with all of that in mind, let's now write out the reactions. So for our anode, reading from left to right, Al is oxidized to Al3+. And when we write the reactions out, when we write the actual reactions out, then we do have to balance it for charge. So to balance for charge, we'll have to put 3 electrons on the right-hand side of this equation. Then for the cathode, we have Cu2+ going to Cu, right? So it's reduced to Cu. And again, when we write out the actual reactions, we have to balance for charge. I have to put 2 electrons on the left-hand side of this equation to make that balance out. Then we could also write the overall reaction if we wanted to. And to accomplish that, you'd have to get a common coefficient in front of E-. That would be done by multiplying the aluminum half reaction by 2 and multiplying the copper half reaction by 3. And so you see that from actually writing out these reactions, you can recover what all the coefficients are. It's unnecessary to include that information in the line notation because you can determine that simply by writing out the actual reactions and getting the overall balanced reaction 2Al plus 3Cu2+ goes to 2Al3+ and 3Cu. And there we have it. So this is how you can take the line notation and decode it into what the reactions are that you have. There is another thing that's important for you to be aware of with the line notation, and that's what happens when you have a redox pair that's completely in aqueous solution. So both the reactant and the product in one of the half cells is in the same phase. In this line notation, what we have at the anode is pretty standard for what we've seen in the previous 2 examples. Ag solid going to Ag+. Right? So that's pretty normal here for our anode. But for the cathode, things are represented a little bit differently here. Because for the cathode, what we have is that Cu2 plus is being reduced to Cu plus. Both are in aqueous solution, and because both of them are in the same phase, we do not separate them with a vertical line. Instead, we separate them with a comma. So that is our cathode here. And then we have a vertical line and then PT. So what this represents, PT is platinum. That's a solid. And the platinum is just a wire that's being used to provide electrical contact with the solution. The platinum itself will not take part in the reaction, so we're not going to write platinum in the reaction at all. The platinum is just there as a wire to provide electrical contact with the solution so that electrons can flow into this solution. With that in mind, let's write out the half reactions for this cell. So for the anode, right, that is pretty standard with what we've discussed in our previous two examples. Ag goes to Ag plus, and you need an electron to balance the charge. At the cathode, what we have is, again, we always read everything from left to right. So Cu2 plus is going to Cu plus, and to balance for charge, we need one electron on the left-hand side of that equation. That gives you the overall reaction. Ag plus Cu2 plus goes to Ag plus Cu plus. And that's how we're able to decode that. And that's how we would represent an electrochemical cell when you have a situation where one of the half reactions is all homogeneous. Everything is all in the same phase. Now, just to get a visualization of what it would look like to have a cell like this, where you would have the redox pair at the cathode that's all in aqueous solution, and to show why you need the platinum wire to make this happen, I have a visualization here that shows our cell. So we have at our anode the Ag and Ag plus, and electrons are going to flow from the anode over to the cathode. But you have to have some electrical contact, right? There has to be some place for the electrons to contact your solution of copper 2 plus and copper plus. And so that's what this bar of platinum represents here. The platinum is not taking part in the reaction. It's just allowing the reaction to happen by providing electrical contact. Next up, we will review oxidizing and reducing agents and talk about how information about that can be used to make predictions of spontaneity for chemical reactions.